Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss energy released during alpha decay and beta decay. Let's begin. In case of radioactive elements, these radioactive elements try to emit radiations. Why they emit radiations? The radioactive nuclei are unstable due to the neutron proton ratio in their nucleus, and these unstable nuclei are tried to be stable by radiating radiations in the form of either alpha decay, beta decay or gamma decay. And during that radiations, a huge amount of energy also released. In that session, we discuss during this type of decays, what be the amount of energy released. First, energy released during alpha decay. When alpha decay occurred, in that particular case, the daughter nuclei we form have the mass number of the daughter nuclei decreased by 4 unit and its atomic number decreased by 2 unit. X having the atomic number Z and mass number A, that is the parent nucleus. Under that of alpha decay, the daughter nuclei form. Let Y be that daughter nuclei. It has the atomic number decreased by 2 unit and mass number decreased by 4 unit. Alpha, that is doubly charged helium nuclei, helium 2 He4. Y, the daughter nucleus, helium as alpha particle. In that of alpha decay, energy is released. Let Q be the energy released. And that released energy is in the form of the kinetic energy of that of daughter nuclei and also the kinetic energy of that of alpha particle. Here we mathematically calculate that energy released Q. Therefore, the energy released during alpha decay, that is given by Q is equal to delta M into C square, whereas delta M be the mass defect. According to Einstein's mass energy conservation, that mass defect is in that form of energy. So the energy released during that of alpha decay is equal to mass defect into c square, c with the speed of light. That is Q is equal to, so mass defect, this is the mass of parent nucleus. Here mass reduced, that is mass of parent nucleus MP minus mass of daughter nucleus My and mass of alpha particle M into c square, where M of P, that is mass of parent nucleus, My mass of alpha particle, sorry, mass of daughter nucleus. Small m mass of alpha particle. And these masses due to that energy released is used in that of kinetic energy of daughter nucleus and the kinetic energy of alpha particles. That expression Q is equal to MP c square minus My plus M c square. Let an equation number 1, the energy released is used in the kinetic energy of daughter nucleus and alpha particle. Let kinetic energy of daughter nucleus is equal to E y, that is half mass of daughter nucleus My. Let velocity of that of daughter nucleus capital Vy square. Vy stands for velocity of daughter nucleus. Next, kinetic energy of alpha particle and kinetic energy of alpha particle. Let capital E, the kinetic energy of alpha particle is half mass of alpha particle m and velocity of alpha particle small v square, whereas small v with the velocity of alpha particle. Equation number 2, that is equation number 3. Therefore, as we write, the energy released is used in the kinetic energy of daughter nucleus and alpha particle. Here the energy released, and that one is the kinetic energy. Therefore, Q is equal to Ey plus E. Ey half my Vy square plus E half m v square. Q is equal to what will the value of Vy that can be calculated by using law of conservation of linear momentum. Here we apply law of conservation of linear momentum. According to law of conservation of linear momentum, the initial momentum is equal to final momentum. In that of situation, initial momentum as a 0, that parent nuclei is at rest, so the velocity of parent nuclei 0, so the initial momentum 0, and final momentum, that is the momentum of daughter nuclei and momentum of alpha particle. Let momentum of daughter nuclei mass into velocity, mass of daughter nuclei and velocity of daughter nuclei plus momentum of alpha particle, mass of alpha particle, velocity of alpha particle. Therefore, m v is equal to minus my Vy. That indicates the daughter nucleus must have velocity in the direction opposite to that of alpha particle. It indicates the daughter nucleus must have velocity in a direction opposite to the alpha particle. mv. From that relation we can find out the value of Vy. So, half my in place of Vy we substitute minus mv divided by my whole square plus half mv square, or q is equal to half m square v square, 1 my cancel out, plus half mv square. Here we can take common half mv square. So we have small m divided by my plus 1, or q is equal to that one is E. This is the energy, kinetic energy of alpha particles, 1 plus m divided by capital My. So the energy released in terms of its kinetic energy of alpha particle. Therefore, alpha particle energy that is E, which is less than the disintegration energy. Disintegration energy Q, that is the energy released during that alpha decay process. Here is the alpha decay process, parent nuclei, daughter nucleus, alpha particle, the energy released, and that energy released in the form of kinetic energy of daughter nucleus and alpha particle according to Einstein's mass energy conservation. Due to Einstein's mass energy conservation, del m c square, that energy is nothing but the kinetic energy of daughter nucleus and alpha particle. Here we use according to the law of conservation of linear momentum, and finally the energy released during that alpha decay. Next, energy released during beta decay. Similarly, beta decay is a spontaneous process in which mass number of the nucleus remains unchanged, but the atomic number changed by unity, and the change in that of atomic number is due to the emission of an electron or emission of a positron or by capture of an orbital electron, which is called K capture. Due to this mode, that beta decay process have three types: beta plus decay, beta minus decay, and K capture. In each case, we discuss what be the amount of energy released. First, electron emission, beta minus decay. See the initial nucleus Z A, the daughter nuclei Z plus 1 A, that mass number same and atomic number increased by 1 unit. Electron, antineutrino. In that particular situation, beta minus decay, a neutron is transformed into proton. That neutron 0 n1 transformed into proton 1 p1. With this, an electron as well as an antineutrino is produced. So in this case, an unstable neutron changes into a proton with the emission of electron and a antineutrino. That is the beta minus decay process. During that beta minus decay, what amount of energy released? Let me calculate. let mass of that initial nucleus ZXA is equal to mass capital M. This is the notation. In notation form we write the mass of that initial nucleus. This is the mass number, atomic number. Mass of final nucleus Y Z plus A, atomic number. This is the mass number. From that of Einstein's mass energy conservation, we calculate what amount of energy is released. Therefore, energy released during beta minus decay which is Q beta minus is equal to mass defect into c square. Here is the mass defect, the mass of initial nucleus A Z minus mass of daughter nucleus Z plus 1 minus mass of electron Me, see the mass of electron, into c square. If we use the atomic mass, if atomic mass M, then we neglect the mass of electron. The mass of electron M of E. Therefore, energy released during that beta minus decay is equal to, for atomic mass we prefer M Az minus M A Z plus 1 c square, neglecting that mass of electron. In an atom, the mass of that atom is nothing but the mass of the nucleons, mass of a proton and mass of neutron. When we considering that atomic mass, so we neglecting that mass of an electron here. This amount of energy is released during beta minus decay process. Another type of beta decay, beta plus decay, that is positron emission, called beta plus decay. This is the parent nuclei, daughter nuclei, its atomic number less by unit 1, positron is created, neutrino is produced. In that of situation, a proton is transformed into a neutron. A proton sends to a neutron and then a positron and a neutrino. So, in this case, an unstable proton changes into neutron with the emission of a positron and a neutrino. Calculating the energy released, therefore, energy released during beta plus decay that is Q beta plus is equal to, according to Einstein's mass energy relation, mass defect, mass of this Az, this is the notation, minus mass of daughter nuclei, mass of positron same as that of mass of electron, c square. In terms of atomic mass, that energy released during beta plus decay. So Mn, we write M Az minus, so the mass of an atom, the mass of the nucleus minus mass of electron present here in that of parent nucleus. This is the mass of atom minus mass of electron, so the atomic number to mass of electron. Next, minus for that of daughter nuclei, minus Z minus 1 into mass of electron. Next, minus mass of electron multiplied by c square, whereas q beta plus is equal to, in that of expression, minus zme and plus me, so minus me plus me cancel out, so mass of Az minus mass of Az minus 1 minus 2Z me into c square. So this amount of energy released during beta plus decay. Next, electron capture. This is the parent nucleus. When it capture an electron, then it is transferred to daughter nucleus and a photon is released. In that of situation, a proton in the nucleus is converted into neutron. That proton is converted into neutron due to capturing an electron in that of nearby shell, capture of an orbital electron. Therefore, a neutron plus a photon is produced. Next, calculating energy released during that process. Therefore, energy released during electron capture, is QE. So the mass defect into c square, here mass of that parent nuclei Mn Az plus mass of electron minus mass of daughter nuclei Z minus 1 into c square plus h nu, that h nu let we call binding energy of k electron of that of atom. Here Be stands for binding energy of k electron of the atom. Again, in terms of atomic mass, we can easily write it as the energy released during that electron capture QE. Here is m a z minus atomic number into mass of electron, that be the nuclear mass, minus in that of daughter nuclei m a z minus 1 plus z minus 1 times of mass of electron plus me into c square minus be, or QE is equal to m a z minus m a z minus 1 c square, that z me minus here z me plus cancelled out be, that be the expression for energy released during that K capture or electron capture process. So here, with the help of this video lecture, we understand energy released during alpha decay and beta decay. First, energy released during alpha decay, this is the mathematical expression. Next, energy released during beta decay, it is of three types. One is electron emission, beta minus decay. Next one is positron emission, beta plus decay. And final one, electron capture, which is known as K capture, its energy expression. So, with this useful and informative notes, let me wind up the session. Thank you.